Right, so you will need your Ackermann worksheet uh, for this video. This is the Ackermann function worksheet. Let me just set things up, where am I going with this? So in the previous video, we had a slide which made the case that you could augment the union find data structure with the path compression operation. And when you do that, you get a complexity of an individual operation that is proportional to the inverse of Ackermann's function. Okay? And what I said was that the inverse of Ackermann's function grows very slowly. And I want to sort of impress you with the behavior of all of this. Okay? And so the thing is, people don't get very excited with small things or slowly growing things, right? Unless they cause pandemics or whatever, right? But what I think is more useful is, why don't we take a look at the regular Ackermann's function, right, without the inverse. Now, as an analogy, right, we know that the inverse of the log function is the exponential function, right? And the log function grows slowly, and correspondingly the exponential function grows pretty fast. So if we're saying that the inverse Ackermann function grows even more slowly than the log function, we're certainly expecting the uninversed Ackermann function to grow way faster than the exponential function, okay? And so that's the point that we're trying to explore with the worksheet. Again, this is, if you sort of grab this before we adjourned, it's the green worksheet on Ackermann's function. You should actually be able to fill this out. Right? There is a recurrence relation consisting of 3 parts that helps define all the elements in this table. We call this table A. And so my suggestion here would be to really pause the video, take this seriously, okay, and see if you can work this out on your own, right? And yeah, I'm going to go ahead and do this right now, but I think you would be well served trying to do this on your own. Okay. So, so let me get started with by taking a look at what's up with all of this complication with the 3 versions of Ackermann's function. So what you really want to be somewhat focused on here is the conditions when you can use different parts of this. So equation 1 is used when the first variable is 1 and j is any value that is 1 or greater, okay? The second version of this is used when the second term here is 1 and the first is any value of I that is 2 or more, okay? So in some sense, this is talking about the first row of the table. This is talking about the first column of the table, ignoring the top left entry, okay? And case 3 is actually the hardest case, is talking about all the other scenarios. So in some sense, think of these as kind of like base cases. They aren't exactly, but that's one way to think about them. Okay, so dealing with the first row seems to be the thing we should do first. And if I look at this equation, all it's really saying is that A1j is simply 2 to the power j. Okay? So A11 would simply be 2 to the power 1. Right? And A12, like when j is 2, would be 2 squared, and 2 cubed, and 2 fourths. And so really all this is a simple exponential on the first row. Okay. Now, how do we think about the first column? Okay. So if I look at this formula, what this is saying is that AI1 is equal to I minus 1, meaning I go one row up, and then here I have a 2, which means I go 1 to the right. So the value over here is actually equal to whatever is over here. So I basically get to copy this like that. Okay. And the same thing would be true here. So if I knew what I had here, I would simply copy it to give me A31, and that's the pattern we will be working with. Okay. So we already know that this, by the way, is 2 squared, right? Because we just copy it from here. Now this is where things get interesting. Okay. And because I now want to try to figure out what A22 is. So this is where, I mean, there's no other way to do this, I think, than to bite the bullet and to start plugging things in. And so A22, okay, and half the battle here is just doing this correctly. So remember, I and j are both 2. So 2 minus 1 is 1. And then I sort of have this recursive A inside this. I have a 2 and a 1, and that's what I get for A22. Okay. After I do A22, I want to do A23. So while we're kind of working with the formula, let me write that down as well. So A23 is going to be A1 and the second term here is A22. So obviously we're not done yet, right? But we're seeing a bit of a pattern emerging. So if I were to go down to A2K, I am going to get A1, A2, and K minus 1. Which, by the way, the A2 K minus 1 is what would appear just above this, right? Because I have 2's on the left, and then over here I'm just increasing 2, 3, 4, 5, 6 up to K because I'm planning to walk along the elements of this row. Right? Now here's the question. What is A1 comma something? Right? Go back up here. A of 1 comma something is 2 to the power of the something. Okay. So therefore, this is going to be 2 to the power A21, which was 2 squared, right? So this is going to be A to the power 2 to the power 2 squared. Okay. So 2 to the power this. Okay. And then what's A23 going to be? It's going to be 2 to the power whatever is in A22. In other words, the value here. So this is going to be 2, 2, 2, 2. Remembering that we are evaluating in this direction. So by the way, how much is this? So this is 2 squared is 4. Right, and then 2 to the power 4 is 16. So that's what you get there. And then this would be 2 to the power 16. Okay, which as a good computer scientist you should know is 65,536. Okay, but then this is going to be 2 to the power whatever this value is, which is 65,536. Okay, and then the next is going to be 2 to the power whatever this is, and I honestly, I mean, I'm good, but I don't know what this is. Okay, So that's how crazily fast this explodes, right? You can see it's much more intense than a regular exponential, and we're just in the second row, right? I mean, if you kind of go deeply down here somewhere, I mean, things are going to get very intense in terms of how incredibly fast Ackermann functions grows. Remember, this is Ackermann's function. It's not the inverse of Ackermann's function. Okay? And so what that means is, if you're very impressed with the growth of this, you should be equally impressed with the very, very slow growth of inverse Ackermann function, which is a representation of the complexity for the disjoint sets data structure. Okay, I think that should complete this worksheet and this week's videos.